is from Alberto Ceschin from KAUST University in Saudi Arabia. And as soon as we have the presentation here, the stage is yours.
Okay. Good morning to everyone. Thank you for being here. So we present some of my recent validation I conducted in OpenFOAM. So we all know about the problem of global warming and how governments are trying to find some alternatives, and most in detail about carbon dioxide capturing. And one way to do carbon capture could be the sublimating the tail gases on a cold surface or a cold liquid in order to filter out the solid CO2. Of course, there's a whole project, and it's way more complex of how I simplify it now. But for now, we are just focusing on frost deposition on a cold surface. So we start conducting the experiments at KAUST. Here, there's a very cold copper coin, and there's a tail gas entering in this chamber. And we see that the CO2 is depositing on the leading edge of the coin. And we see that this process, the frost form, is porous, is not uniform in all the copper coin, and it has a transient component. So we cannot really use a similarity solution and some analogy from heat and mass transfer. And we would like to find a more general approach to use this model also for other geometry, and inserting maybe a liquid also to better mimic the process itself. So we start looking into CFD, and there's a lot of work that has been done already with water and ice. And today we can see that if we have a cold surface with time, we have humid air, we will have droplet nucleation at first, and then dendritic growth. There's no, we are not crossing the liquid region, so we are neglecting about droplet nucleation for now, and we are taking care about that for frost that is that will occupy a portion of our volume in our computational grid, for example. So we can define a color function that is the frost fraction inside our computational cell, and then we can solve an ODE for this frost fraction, and we will have that the frost densification and growth is given by a certain rate. This rate will be for sure proportional to the saturation rate according to equilibrium. And we can add also one more contribute from the Stefan number. And we end up that is just the difference in enthalpy divided by the latent heat. And we end up with another gradient of temperature that is another driving force that is especially important at lower temperature. So we can design a new solver, and we can solve for the vapor mass fraction. Then we can recover the air from stoichiometry. We can resolve that ODE to get the mass of ice that is growing. Then we can get the latent heat of the sublimation that will be part of our energy balance. We can solve, of course, then momentum, and that only for the gas phase. We will have a drag form, a drag term that can be called Darcy for another contribution. And it will represent the cyclical velocity when the flow is entering inside our frost. And of course, we can solve, we need to solve for continuity. There's a little catch if we look at a flow, for example, on a cold surface. If we look at the temperature profile, we see that we could be under the sublimation point, also in middle air, but of course we don't have frost formation in middle air. So we need to somehow to limit our phase change. And there are two approaches in literature, always for water. And it's either to build a complex relation from experiments, where we basically cut the mass transfer rate if we are far from this frost layer, or we can use the information of the cell next to our computational cell and see if we are either attached, if either the cell is attached to the cold surface or it has some frost already next to it. I choose the second approach, and my function is just the gradient of temperature, but on purpose I put in these two complex formulations that are derived from experiments, just to show you how in this field we still heavily rely on experimental data. So, of course, I started ambitiously with a conjugated transfer solver, multi-region, but my simulation was taking probably three months. And the problem is that the experiments are also like 3 hours long, and if you have a flow over a surface, my time step was in the order of 10 microseconds. So I removed the solid region, was taking probably 1 month, the simulation. And I had to do something more. Of course, you increase the CFL number, but if you increase it, you have flow separation, and mass transfer is not evaluated anymore properly. So what I came up with was using subcycling, and in kind of a peculiar way. I used a larger time step for all the equation, but the pressure velocity coupling that I moved at the end of the outer loop. What I do is I use, of course, the previous values of velocity for the equation. But okay, before the outer loop, I mark the cells where I want the mass transfer. Then I start the outer loop. I want to evaluate the saturation condition for the molar fraction. So I can solve implicitly the vapor mass fraction. That was the most important, not to have overshooting of the mass fraction beyond the physical field. And then, implicit solution of the vapor mass fraction equation. Then implicit also for the simple ODE you saw before. With this equation, I can recover the latent heat, the temperature equation. I can initialize the quantity that will be divided, and only a fraction of them will be added to each sub-cycle that I will do of the to finally solve the Mashimov's problem. So these are the results, and I must say that this works only because the flow pattern is not changing much. If we start to have something that doesn't look like a potential flow, this approach won't work. But if we look here at the plot, that is the first thickness in time, we can see, so if with one, I have no subcycling, so I'm solving for the same time step. Increasing the number of subcycles means that, for example, with 40, the temp energy mass, vapor mass are solved for a CFL like of 40, and at the end, the pressure velocity coupling is solved for a CFL equal to 1. We see that up to 40, the line overlapping has really small difference. But if we still increase the global time step, we have this weird behavior because we have separation, so we can't evaluate properly the mass transfer because we have recirculation inside, and the frost is not thickening anymore much. So again, as you may understood, I couldn't do I couldn't do modeling directly on carbon dioxide because we don't have a reliable experiment. So I worked with frost and water. Of course, we are crossing the liquid region, but at this stage, we are not taking account of it, and we can model equilibrium between the gas and the solid from a simple Raoult law to evaluate the equilibrium condition and use this to build the gradient that will be our driving force. So this is a simple case study. We have a flow straightener, so we'll assume a straight velocity profile that is entering the channel with a cold copper plate. Since we are doing a lot of cycling with the pressure velocity coupling, I brute forced the pressure solver just to see which was the best combination that could have. And I did some grid independent studies, and it seems that increasing the resolution, the frost thickening is collapsing to one. That it's nice. So here we can see some results. Here we can see the leading edge that has a higher density, and we can see how the momentum is because of the drag turn is reducing, so the cycle frost will be mostly driven by diffusion. So I did some validation with experimental data. So the continuous line is my result. The dashed lines is a 1D semi-empirical model, and the dotted line are experimental results. I evaluated the frost thickening since just as an algebraic mean of the top coordinate of the layer as soon as I had some frost on it. I assumed that as a local value, and I did algebraic mean. So we can see that we are capturing pretty well the experiments. Of course, in the initial area, at the initial time, we are a bit far if the temperature of the plate is relatively warm. That's because we are not considering nucleation of droplet, whereas at the lower temperature, basically all the boundary layer is frosting. If the temperature is the part of the boundary layer with the temperature frost below the exclamation point is frosting immediately. So we don't even need almost that threshold condition that I showed you before. Here some other validation. If we increase the humidity ratio, relative humidity, we can see that we have a thickening that is faster in time. So these are my results and overview of the implementation I did inside OpenFOAM. I liked a lot the subcycling part that seems to work very efficiently for this case. I started with a 3-month simulation and end up with a 12-hour simulation that I will consider a success. And mass conservation was always, I mean, the difference between the fluxes and the integral of the ice and the gas of the water has sublimated already, and what was in the domain, that difference was always below 0.3%. So mass conservation is also proved. Of course, I want to move to lower temperature, and there are already experiments. Because we can neglect that condensation part of the droplet. I want to move to CO2, but we are still doing the experiments. And I want to move to a flow over a cylinder because the process, the cryogenic carbon capture, we have in mind, and it's working already on pilot plants, has a countercurrent spray of isopentane at very low temperature with the tail gases in order to have the carbon dioxide that is depositing on the surface of this droplet. So we can collect the slurry on the bottom. We can screw press to extract the solid phase that is our CO2, and the liquid can be recycled in this countercurrent tower. And yeah, of course, at the end, I want to derive some submodel that are applicable to a Lagrangian larger simulation of this spray tower. And with this, I will thank you, everyone. And if you have any question, please.
So thank you very much for the presentation. Is there any question from the audience here or online? Yes, please.
Thank you for the presentation. So if I correctly got your point, if you want to optimize, let's say, the geometry of your copper plate, for example, you would need to rely on some dedicated experimental data, which is correct, if you want to properly optimize.
So the correlation. Okay, if I need experiment, if I want to change the geometry, I would need more experiments on that special geometry. Correct? Okay, so that was the starting point, but what I want to do is to find a more generic correlation that once I proved valid on a copper plate and would work also, for example, on a copper rod, so I can use it for whatever geometry I want, because I know usually you look at the global quantity, you evaluate Reynolds, Nusselt with correlation based on the geometry. But we are in a direct numerical simulation context, and I want to find some correlation that is proved to be valid also in a smaller scale.
Thank you.
Any other questions from the audience here? Then let's thank the speaker again. So now we're going to have the last presentation for this session from Dario Colombari for the Università Cattolica del Sacro Cuore.
Okay. Good morning, everyone, and thank you for being here. My name is Dario Colombari, and I'm a PhD student of Università Cattolica and Politecnico di Milano. In today's presentation, I will be giving you a very brief overview on the future application of OpenFOAM for the thermal simulation and management of livestock buildings. I will begin by filling in on the motivation and the objective behind these activities. Then we will move on and we will be taking a look at the modeling strategy we have adopted and to some sample simulation results. At the end, I would like to highlight some of the main points of this presentation. So let's get started. Do you know that in hot and humid environments, dairy cows are likely to lose up to 40% of milk production? We are talking about 15-20 kilograms of milk every day from each cow, and it's a huge quantity. You can imagine the economical effect of this problem. This problem is called heat stress, and it's triggered by the imbalance between the metabolic heat generated by the animal and the heat transfer with the environment. Besides a reduction in milk yield, we also have very low levels of animal welfare and several health issues for animals. It's clear that as heat stress is connected, is spark off from very hot external conditions, the ventilation system and indoor conditions for barn are extremely influential. The ventilation system of a livestock building must be correctly sized and designed in order to have a good productivity of the animal. Current state-of-the-art methodologies for barn design are based on very simple models, for example, mass and energy balances on the wall building. And of course, they are pretty inaccurate and not fully predictive. Well, is it possible to do better? Yes, but we need to use some more complex models. For example, computational fluid dynamics. This brings me to the second part of my talk, that is about the modeling strategy and of a livestock building in CFD. We are currently working on the CFD simulation of the ventilation system of the Research Center for the Technical Activities located in Piacenza. On the left, you can see a picture of the real barn, and on the right, the computer model we are working on, just to know the geometry. The modeling of a livestock building in CFD is a complex multiphysics problem. We need to consider lots of factors. First of all, we need to consider the effects related to the air change rate inside of the building. So we need to consider reduced ventilation, recirculation fan, of course, and also buoyancy-driven flows. We also need to consider the effect influencing the thermal field. So we need to consider solar load and, of course, the animal thermal load. We also need to consider humidity, as it is one of the factors that influence the degree of animal welfare. We are currently working with the easy version of OpenFOAM, in particular with the version 22.06. And we are working with a custom incompressible solver. Buoyancy is modeled following the same methodology of the buoyant business input form. So we are considering constant density and a variable volumetric vector mass force acting on the fluid. As we are working with an incompressible solver, we cannot directly model humidity, but we are considering humidity as a transported field. In addition, as we want to consider wind-induced ventilation, we need to consider the atmospheric boundary layer. And we are using the atmospheric boundary layer family of boundary condition from OpenFOAM. The main challenge in the CFD modeling of livestock building is animal thermal modeling. Together with Università Cattolica, we are working on an innovative approach based on the animal energy balance. We can estimate the energy take of the animal, starting from the matter intake of the animal, and we can estimate the solid and liquid residuals together with the energy content in the air. By closure of the balance, we can compute the thermal loss of the animal. And starting from the thermal loss, we can compute the average metabolic heat of the animal, that is around 2 kilowatts for each animal. Of course, once we know the thermal load of one animal, we need to scale up to the whole power balance simulation. We are considering animal using a simplified approach. Of course, this strategy has been used in order to reduce the computational cost. We are considering animal as uniformly distributed energy source term placed inside animal occupied zone. We are just using let's say an FB option derived from the scalar implicit source of OpenFOAM. We are considering more or less 70 animals in beddings, and 30 animals in the feeding line. The number of animals has been estimated starting from consideration based on the time spent by each animal in each region of the barn. Another interesting aspect of the simulation of livestock buildings is the modeling of the ventilation system. We have around 40 ventilation devices, including 30 high-speed fans and 5 chimneys. We are modeling all ventilation devices as disc-shaped cyclic patch with a custom version with particular boundary condition derived from the cyclic fan and the uniform jump end. The pressure difference between the two sides of the cyclic patch has been computed starting from the thrust of the fan that has been measured by the manufacturer. Another relevant effect is solar radiation. And of course, we need to consider the heating effect of the solar radiation on the barn. We are using solar load model present in the easy version of OpenFOAM in order to add surface energy source term on exposed surface of the barn. We are also estimating the conduction through the roof of the barn by using a modified version, an incompressible version of the thermal baffle 1D boundary condition. So let's turn now to the simulation results. We are performing simulation in two different conditions, winter and summer. This is simulation in winter condition, and we only have the eating effect of animal, so the source of gas, and buoyancy. Solar load is not considered, as well as with induced ventilation, and also the recirculation fan are turned off. Why are these conditions interesting? Well, this is the ventilation and the air change rate generated only by natural convection and by buoyancy-driven flows. So this is the minimum air change rate you can have in the building. Of course, we need the minimum air change rate because it is our benchmark for the improvement once we turn on the ventilation system. On the left, you can see the velocity field and the creation of buoyancy-driven flows inside of the barn. And on the right, you can see the temperature field with the thermal solidification due to buoyancy. Of course, we are interested in winter conditions, but the most demanding conditions are summer ones. In this case, we are considering high external temperature, it is 30 Celsius degree, and high external relative humidity, it is around 50%. In this case, we are considering both wind, solar load, and the ventilation system is turned on. And you can see high-speed flows generated by the fan. This is even more clear when looking at theoretical results from a top view. This is an horizontal slide at a few meters of height, more or less. And you can see that recirculation fans are all blowing in one direction. This is actually wanted by design because we want to use the recirculation fan in order to create air entrainment and enhance the air change rate in the building. You can also see that wind is actually changing from the desired path up wind fans that are set ones. Of course, we are also interested in the thermal field, and you can see the heating effect due to the presence of the solar load on the top of the barn and also under the barn because of conduction. And of course, you can also spot the heating effect in animal occupied zone due to the presence of the animal thermal load. A similar effect can also be seen when looking at the humidity field, as you can see, an increased humidity in animal occupied zone. Well, at this point, we know the temperature, humidity, and velocity in each single point of the barn. But how it is possible to estimate the thermal comfort for animals? Well, several authors in literature have correlated animal physiological condition, for example, respiration rate, heartbeat, core body temperature, with the external conditions. Well, these authors have created a corrected temperature called effective temperature index for dairy cows that give us the benchmark of the thermal welfare for animals. The threshold in order to have the first effect of heat stress is around 26. As you can see, external conditions are critical for animals. We have around a value of 28, so animals are likely to suffer from heat stress. Nevertheless, due to the presence of high velocity air flows inside of the barn, we do have a value of around 25, which is under the threshold. In this condition, animals, well, inside of the barns are likely not to suffer from heat stress, and the ventilation system seems to be quite effective. We also have some, of course, some problems. You can see that we have a very strong ventilation in the central region. Well, in the feeding line, we have just few animals and we have lots of fun. Of course, in this configuration, we are providing a very high air change rate to very few animals. Well, of course, this is fine for these animals, but of course, we are just wasting lots of electricity. And you can also see that we have in some other regions some hotspots due to the presence of stagnation zone. Of course, this is not good for animals as we expect to have some animals that are performing well with very high productivity and some animals starting to suffer from stress. So to conclude, I'd like to highlight some of the main points of this presentation. Let's see that animals require correct thermodynamic condition inside of the barn. We need the correct temperature and humidity indoor. The ventilation system of a livestock building must be correctly sized and designed in order to grant these conditions. Fluorescent methodologies are not accurate, but we can use computational fluid dynamics. CFD is a great design tool for the ventilation system, especially for livestock buildings. And the application of CFD for the thermal simulation and management of livestock buildings will lead to an improvement of animal condition, first of all. That also means higher productivity and also minimum electricity consumption. So, all in all, the application of CFD to the technical sector may help both the sustainability from an economical, an ethical, and an environmental point of view. Thank you.
So thank you very much for the presentation. Do we have any questions in the audience?
Yeah, that's great, very good. To make your work more accessible, that you plan on making it the average Genoa engineer can use in designing the barn to make your work more accessible. Yeah. The Livestock project is actually to develop the equivalent 1 meter model, calibrated starting from the data from scale, in order to simplify. A simplified 1D model will actually be used in very short time and much more accessible. In addition, NVIDIA is going to, maybe I should speak
Closer to the mic.
Yeah. Okay, just to repeat the question, which is the plan to increase the accessibility and also for the applicability on a, let's say, fast scale of the model, more or less? The CFD model can be used to calibrate one simplified 1D model of the barn. So to calibrate the model that are already used, so mass and energy balances to wall building. And in addition, we have made quite a lot of work in order to keep the computational time quite low. We are working basically on a standard workstation, and the simulation time is around 2 days. So it's quite good. It could actually be used in industry. It is not something that is strictly connected to the research sector. Okay.
Out of curiosity, is there, and like we have for people building some regulations regarding the thermal comfort, is there any, like from the ISO regulation and so on, is there anything similar for?
More or less, there are some guidelines. These guidelines are not strictly connected to the degree of animal welfare. There are something, but these are not approved yet. It's something that is, let's say, it's a work in progress from the European Union. And there are some guidelines about the air change rate in buildings. And it is connected not especially to thermal management, but to the air quality. And it is especially connected to the air quality for the workers inside of the barn. Another aspect is related to the ammonia emission from barns. That is a relevant problem. And indeed, it will be one of the aspects we will work on in the future. And in this case, we have a minimum and a maximum air change rate that we can have in the building in order not to have a too high concentration of ammonia inside of the building and an excessive emission of ammonia from it. So there are some guidelines. There are no regulation, but guidelines. So
Interesting. Thank you. Please.
Yeah.
Thanks for your call. So typically those bars have, typically those bars that walls that are open pipe. Yes, we got our roof and the second, they got a roof. So typically when they're swing, the wind speed and also wind direction. But normal, influence out of needs this to that part. That you,
Let me repeat the question to the people at home, and I have more or less a backup slide of these. Well, the question was, which is the effect of wind-induced ventilation and or how to model it? Well, of course, we are considering wind-induced ventilation through a logarithmic inlet velocity profile. That's from the atmospheric boundary layer modeling strategy. In addition, we are considering different barn orientation in comparison to the wind direction. For this reason, we are actually using this kind of layout for the mesh. The barn is actually snapped inside there, and around here we have a rotating hemi. In this case, before the start of the simulation, we just change the rotation of the barn in comparison to the wind, and we use just a standard logarithmic inlet velocity profile from here. In addition, the idea, it is not something we have already done, but it is something that we will do for sure, is to perform a sensitivity analysis on wind speed and wind direction. To be honest, the region of Piacenza, where the barn is not windy at all. I mean, the average wind velocity is around 1 meter per second. So we do not expect to have lots of problems related to wind. In any case, it's something that for other applications, for example, a barn placed somewhere else, it will be important, and it's something that we have considered. In addition, we have also considered the presence of some side buildings near. Indeed, we are also considering this building here that is next to the main body of the building. Of course, we should have included other, let's say, other buildings inside, trees, and so on. But of course, we aim to have the minimum computational effort possible in order to make it accessible for the industry. Okay? Yeah? Yeah. Yes. Yeah, we're working with, if I remember correctly, let me repeat the question for the people at home again. The simulation time was about a couple of days, and we have 5 million cells. And how it is on which computer we are working on? Well, we are working on the simulation cluster of Politecnico di Milano, and it is around 30 cores, if I remember correctly. The simulation was on 30 cores. 30, yeah, yeah. But you should also consider that this simulation is basically a steady state. So of course, the change in time is not so relevant for a long time. We aim to have the average condition. So the capability of running on steady state helps quite a lot in reducing the computational time.
So the fancy curve is the
Yeah. Well, we did have quite a lot of problems related to the instability. So we have adopted quite a small, let's say, time step in order to have a numerical stability. We are working with a time step that is 0.01 seconds, because we have lots of higher speed and we have lots of gradient and quite large cells. So the simulation stability is quite a problem. On besides that, we are also using, let's say, of course, we are running the simulation for what we are using, let's say, a quasi-steady approach in order to get the solution. And we are running the simulation for quite a long time in order to be sure to reach the end of the thermal transient of the barn. Of course, we need to consider the presence of the thermal load of animal, solar load, and so on. So we have quite a long thermal transient of temperature inside the different zone of the barn, especially in the region with very low air change rate. So we have simulated the barn for, if I remember correctly, in the winter simulation, the total simulation time was over 1 hour of simulation. So we wanted to make sure. Okay. Any other question?
I was wondering if you try to establish the dependency of your results from the size of the amount of external analysis that you have, because you have yes and natural convection of
we in the current stage of the process we did, and we actually realized that in order to have unluckily, I do not have any results about this, but we started from a much smaller size of external space around the barn, and we managed to find a good compromise with more or less few tanks on each side the side of the barn. So the total space required by the installation is around 250 meters for 250 meters with 80 meters of length. This is another. The optimal values was actually a bit higher for the height of the simulation in the case of natural convection, because in that case we do have driven flows that flows up to the top of the domain, and in this case it did create quite a lot of problem, and if the flow was not fully developed until reaching the top, of course. Okay. Another.
Last one, then we need to close this session.
So previous experience, and that's directly from the song.
We only included direct radiation from the sun, and I know 500 watts per square meter was not a great value. Actually, the real one was probably more realistic, be 100. But we are aiming to simulate an average condition, and we have sampled 1 day in Piacenza, starting from meteorological data, and the average one was around 500. So we have used 500 watts per square meters.
But that's like the reference for
Yes, directly from the solar.
Yes, so if you go to the that is from the environment, you can take more guys to the region.
We have considered the solar radiation starting from the sun position in the sky, and by using the solar rod projecting the trajectories of each face of the patch toward the direction of the sun, and considering of course, considering the cosine between the angle of the face center and the ray projecting toward the sun direction. This is the solar, let's say, the surface heating effect, the surface energy source term due to radiation. we are not considering diffuse radiation at all, and that's a problem, of course.
Protecting reason why we have not stopped there.
Well, one was, of course, simulation time, because we didn't want to make the simulation too complex. Secondly, because we had some problems with animals. I mean, we are just modeling animals with, sorry, for diffuse radiation, do you mean the global diffuse radiation on surfaces, or you mean the adoption of a more complex model, for example, a P1 or something?
It's still solar radiation, what would be what, for example, the sky.
Yeah.
So the radiation that's what people on that. We might form where that happens. Because the storm is going from the other hand, so you're getting that radiation just from that angle. Well, the sky is like surrounding area, so you get more of the sky.
Yeah.
So I'm like, if you consider only what's coming directly from the storm, and so you want that estimating the people from solar radiation. That's the way the function goes. Yes.
The entire square region was the guidance for the entire power and actually considering all the diffuse radiation is something that is actually should be done. So very good observation. Thank you.
Okay, if there is any further discussion, we can use the break afterward, and we need to close this session now. Let's thank the speaker again. Monica.